lecture today. And before we proceed further, let us just revisit very quickly what we discussed in the first lecture. So, the benefits of advanced control theory we are discussing last time, summary motivation and all that. Very quickly, the benefits include first is MIMO theory, that means multiple input, multiple output. Obviously, it is lesser assumptions and approximations. Then we can also design control system which will take care of simultaneously, it will take care of disturbance, rejection and command following. So, these are typically conflicting requirements, however, we will be able to do that. Then we can also explicitly discuss about robustness of the controller in terms of parameter variations, external disturbance, unmodelled dynamics, etc. There are various ideas, modern ideas like fault tolerance, self autonomy, things like that, which can also be we can handle those problems in the framework of advanced control theory. Then we can even talk about optimality of the controller, which traditionally this classical control system do not talk about. And we also can do this explicit trajectory planning issues can be incorporated into the control design in the framework of optimal control, if we talk about. And state and control bounds can also be incorporated in the control design process explicitly. That means, you do not have to live with the error, you can even design the control system based taking into account those bounds if you know that a priori basically. Integrated designs they can replace the traditional outer loop, inner loop sort of structure. That means, you visualize the problem as it is, not like parts of systems and things like that. And then it can obviously lead to better performance. These are called integrated design essentially, or in aerospace industry they are called integrated guidance and control, for example, actually. Okay. Then we discuss why do we talk about nonlinear control, and especially compared to even the MIMO system, MIMO you can design control systems based on linear theory as well as nonlinear theory. So, when you discuss nonlinear control, one of the obvious reason is we want to improve the existing control system. So, there may be some control system already based on linear systems, and you account for nonlinearity and then improve on that. Then we can explicitly account for something called hard nonlinearities and strong nonlinearities. We discussed about that in the last class anyway. Hard nonlinearities include discontinuity in derivatives, that means saturation, dead zone, hysteresis, all that. And then strong nonlinearities are higher order terms in the Taylor series essentially. So, those can be explicitly accounted for actually in the nonlinear control framework obviously. And we can even talk about it can directly deal with this model in uncertainties as well. And it can sometimes it can lead to design simplicity, which is a little bit counterintuitive. The moment we talk nonlinear control, it feels difficult. But some design approaches are available which can even which can be simpler than the linear design techniques. And then there are various techniques that are available, phase plane, Lyapunov, differential geometry. We discussed about all that, and some of these may not be discussed in this particular course, but many of these we will discuss actually. Okay. Then advanced control theory applications in aerospace engineering in particular, there are various applications. But a couple of them which comes to mind is missile guidance and control. Then we can have variety of advantages compared to classical design. So, especially when missile control application, we talk about rapid and precise command following, or rapid and precise, that means you want the miss distance to be as minimum as possible, like direct hit sort of thing. So, any approximation there will lead to compromise in the performance. So, you really do not want to do that actually. That is one way. Robustness is also required against unmodelled dynamics and parameter variations, because typically the parameters do vary and then they cannot be predicted exactly, because weather conditions, for example, you cannot predict exactly before you fly basically. And then multivariable designs they are required due to high coupling, system limitations are there, disturbance rejections are a requirement, and there are variety of challenging requirements, because of which we really need advanced control theory for missile guidance and control. Okay. And next, aircraft flight control, even though a lot of classical designs do exist and many aircrafts do fly in that, but still you talk about modern control theory for variety of reasons, and one is stability augmentation. Whatever stability regions you get, you want to enlarge the domain more. So, you want to see whether you can do that with advanced control theory. configuration management, another issue. That means you already have a baseline configuration, and suppose you want to kind of modify the configuration little later, then entire thing needs to be repeated if you talk about classical design or linear control design actually. So, but if you really talk about advanced control theory, especially the nonlinear control theory, you may not need that actually. So, there are variety of advantages when you talk about aircraft flight control, especially people now talk about reconfigurable control as well. That means, on flight, suppose your part of the wing is gone because of battle damage or something has happened there, then how do you quickly reconfigure yourself and then take your aircraft back to the station. That is one way. Or if you are talking about a commercial aircraft, then at least you should land somewhere safely. I mean, you should not crash actually. So, those are the things, or if possible you can just land it as if nothing happened really. Okay. So, those kind of applications are on the research domain, and these are really advanced designs that we can bring into in aircraft flight control actually. Unmanned aerial vehicles have a variety of applications, for example, reconnaissance for collecting the information from the enemy side, warfare capability, it will again give a different tool for you to apply. Then experimental research becomes easy, because it does not cost too much of money to build a big aircraft, and you quickly can experiment your conceptual ideas there. And many of the academic research, that is the one particular thing that gives us a very good tool for experimenting flight control designs actually quickly. Then there are variety of further applications like autonomous mission. You do not really have to plan meticulously where to go, where to come and things like that. So, you just I mean very rough way you give that guidance, okay. Then after that the vehicle takes over and it actually flies in an autonomous mode. So, those are variety of applications that your unmanned aerial vehicles are kind of important for modern research and all that. And there are again peacetime applications like search and rescue, meteorological data collection, even movie recording. I mean, those are you can just fly over and with a camera and then record a movie maybe. So, those are variety of applications that we are looking for, and aerospace applications not necessarily only 3, there are many other applications as well actually. So, with this we thought we will just we had some proper motivation to go further actually. So, then coming to today's lecture, as we discussed last time, we will revisit this some of these classical control issues and all that before we go for modern control really. So, in that sense this particular lecture today we will discuss about first and second order linear differential equations. So, that is the topic of today's lecture really. Yes. So, very quickly we will revisit what you already know probably in other graduate courses and all that. So, when you discuss about linear differential equations, the very first thing that comes to mind is principle of superposition again. So, if x1 and x2 are solutions of some differential equation, okay, then this alpha times x1 plus alpha alpha 1 times x1 plus alpha 2 times x2 should also be a solutions for any scalars alpha and alpha 1. That is the principle of superposition really. Okay. For example, if you have x double dot plus x equal to 1, essentially remember this is a non-homogeneous equation because it is not equal to 0. Okay. Then very quickly we can verify that 1 plus cos t and 1 plus sin t both are solutions. It's easy to easy to verify. Let us verify quickly. So, we have this x, okay. We have this x double dot plus x equal to 1, okay. All right, and we are exploring this possibility of whether x equal to 1 plus cos t is a solution or not. Okay. So, what you do is you put x dot equal to minus sin t and x double dot is equal to minus cos t. Okay. So, if you substitute it back, then what you get? You get minus cos t plus x, which is 1 plus cos t, and that is equal to obviously 1, right. So, it essentially satisfies the differential equation. So, individually if I take 1 plus cos t, it is actually a solution of this differential equation anyway, and similarly you can verify that 1 plus sin t also satisfies that. Okay. However, if you put both 1 plus cos t and 1 plus sin t, even though they are individually they are solutions, they will not satisfy the principle of superposition. Okay. It's easy to verify actually. So, then let us for example, 2 into 1 plus cos t, whatever you have here, let us verify whether that is there or not. So, simply I talk x equal to 2 into 1 plus cos t. Okay. If you carry out all the algebra there, then it will turn out that okay, x dot is equal to minus 2 sin t and x double dot is equal to minus 2 cos t. Okay. And if you substitute it back, what do you get? Minus 2 cos t, that is the thing, and x equal to 2 into 1 plus cos t. Okay. And that essentially gives not really 1, but that is 2. Okay. So, essentially it does not satisfy the differential equation really. I mean the combined multiplication really does not satisfy. So, what is that actually? I mean this equation is actually very close to linear system anyway. This equation is very close to. However, we should also remember that when we apply principle of superposition, you should apply to the homogeneous system, not to the non-homogeneous part. So, if I make it 0, this equal to 0, then it will satisfy. Okay, you can verify that quickly. All right. So, that is what I told this. If it is x double dot plus x dot equal to 0, okay, then it will very quickly, I mean any solution, that individual solutions if you take, then it will satisfy the differential equation anyway basically. Okay. So, that is what it is. Even x double dot plus x equal to 0, that is the original thing that we started with. Okay. Just instead of 1 I put 0, then it will satisfy again actually. Okay. So, the lesson to remember is principle of superposition even for linear systems holds good only for homogeneous part of it. The entire part it may not hold good actually. Okay. So, that is the lesson to remember. All right. Now, let us go to solving the differential equation. Now, we suppose somebody gives us the first order linear differential equation, then how do we solve that? And we will essentially start with this homogeneous system equation, that means homogeneous system, where the right hand side is actually 0. Okay. With initial condition x of t 0 equal to x 0, and this k that is actually 1 over tau, where tau is typically known as time constant. Okay. So, at this part of the solution we are assuming that tau is constant and hence k is constant anyway. So, how do we go and solve it? It is essentially we know that from close to calculus here, that given this differential equation I can very quickly go to that part of it, because x dot equal to minus kx. So, dx by dt is minus kx. Okay. Let us quickly see that. So, this is x dot equal to minus kx. So, this is essentially dx by dt, this is dx by dt is equal to minus kx. So, that means dx by x equal to minus k dt, okay, minus k dt. So, that is what it is kind of written here. Okay. This dx by x equal to minus k dt what we got here is written here. Okay. All right. Okay. So, let us quickly go to the next part of it. So, once we know that this is dx by this dx by x equal to minus k dt, then we can integrate both sides and then take logarithm of x, natural logarithm is equal to minus k times t plus some constant, and that constant let me write as some logarithmic c anyway. When I take this one to the left hand side, I will get ln of x over c is equal to minus k t, and hence if I take the exponential form, x turns out to be e to the power minus k t into c. Okay. Now, this initial condition we have to apply. Remember, without initial conditions differential equations are not complete. So, only differential equations do not have much of meaning actually. So, now let us try to apply the this initial condition. So, we put t equal to t 0 and then x becomes x 0. So, we get x 0 equal to e to the power minus k t 0 into c. So, c becomes solution of that, which is essentially e to the power k t 0 into x 0. Very clearly from this equation you can see that. And then if you substitute it back in this equation, this c will substitute it back here and then make it complete, and then it becomes x of t equal to e to the power minus k into t minus t 0 into x 0. That is the standard form that we know very well from plus 12, from our previous knowledge actually. Now, let us see what are the implications of that. When we discuss about e to the power something, there is also a exponential form available to us. How do we evaluate e to the power 80? One way of evaluating that is using this exponential form. Okay, I mean this probably power series, you can say that. Okay, that you expand it in terms of power series actually. This is essentially an infinite series, unless at some point of time it truncates. I mean, whether it truncates or not, I mean it depends on how this series evolves and all that, but in general it will not truncate. The moment A is a constant, it will keep on staying there actually. Okay. So, after if A is probably less than 1, then after some power we typically truncate, telling that it has no meaning after that. However, it will never become exactly 0. Okay. And this power series form I have explicitly put here, because this is the form we will need it later for MIMO systems, for modern control things and all. There is also a notation of e to the power a t, where a is a matrix, is not a scalar. So, at that point of time we will need this exponent, I mean this series form to evaluate e to the power a t and all that. That is one way of evaluating that. So, we will see that later as we go along. However, if a t 0 is 0 for this specific case or special case, suppose we just start to visualize the solution at some point of time and initialize the time as 0 at that point of time, then this t minus t 0 will go from here, and essentially we will be living with a much simpler form. Okay, it looks slightly simpler compared to the previous solution essentially. So, we have this x of t is e to the power minus k t into x 0, that is the form that we will typically use all the time, under the assumption that t 0 x of t 0 is, I mean x 0, where t 0 is 0 basically, under the assumption, that is implicit assumption actually. Typically, this first order equations also admit some solution like that, provided this k is positive. If k is really the tau is positive, so k is positive, that means minus k is negative. So, then if you see this solution and all, this solution will evolve like that actually. Okay. So, essentially there are two, if otherwise of course, it will evolve like another way actually. Suppose if it is other way around, that k is essentially negative, then it is unstable, which will go like that. Okay. Or k is positive, it will evolve like this, and then it will go towards 0. Obviously, if k is 0, then it starts with some value and stays here. So, that x dot is 0, it will continue there actually. Okay. So, this is valid for k greater than 0, this is valid for k less than 0, and this is valid for k equals 0 sort of thing. And if it is stable, there are notions of like if I go one time constant away, that means my t evolves by one time constant, then my value of that x naught will decay to almost 63% of what I had initially. These are all very standard results. It is very easy to I mean analyze and see ourselves actually. Next, we will discuss about non-homogeneous equations. That is all about homogeneous part of it. Suppose you do not have 0 here, but let us start with the simple thing, you have some other constant a, then what happens actually? Then the solution evolves in two parts, one is homogeneous part, where this is equal to 0, and there will be a particular solution. The total solution will be part of like homogeneous plus particular solution. So, you have a homogeneous solution coming as it is, that we discussed just now. So, the homogeneous part will turn out to be like that. Remember, I have already written k equal to 1 over tau, because that is the standard form anyway here. Now, particular solution depends on the form that you have here, and if you have a which is a constant here, then the particular solution will also become another constant v, let us say. Okay. So, that is how we start with. Then we substitute this solution back into the differential equation and try to see what is the particular solution, that is the approach actually. Okay. So, we start with this particular solution, a constant b, then this is 0 anyway, derivative is 0. And hence, I put this constant back in there, 1 over tau b is equal to a. So, that means x p, the particular solution becomes tau into a, because remember b equal to tau into a, b is the particular solution anyway. So, what is the total solution? Total solution is this homogeneous part of it plus this particular part. So, that is what is written here. So, total solution is homogeneous solution plus particular solution. So, it takes that form. And now remember that if you have a non-homogeneous differential equation, we must apply the initial conditions for the total solution, not for any homogeneous part only basically. So, we have to apply the initial condition for the total solution basically. So, we have a total solution here. Okay. then we apply the initial condition here. So, at t equal to t equal to 0, I mean t 0, which is we implicitly assume t 0 is 0 here. So, x 0 that is equal to c, because this becomes 1 here, okay, plus tau a. So, if you solve it, then c becomes x 0 minus tau a here, okay, and then x of t we can go back to that, and that is this part of it, because you already have a c known to you by now. So, you substitute it back and then tell, okay, this is my total solution. Okay. So, that is the total solution that you really have, and here remember this part will go to 0, okay. As t goes to infinity, this part will go to 0. So, the x of t will really approach tau times a, it need not approach the a. So, there will be some sort of a steady state error basically, because if you really have this let us say if you put tau and this is your a value, okay, and you start with some initial condition x 0, you need not really go to that particular solution as it is. There will be steady state errors actually, unless tau a is equal to b. Okay. Okay. However, we have already seen that b is tau a anyway here. Okay. That's what it is. So, it will actually essentially go to really b. Okay. There won't be any steady state error. I mean that's the analysis part of it. How do we analyze that actually? Okay. All right. So, that is I mean, but oh sorry, okay. No, there is a small error here probably. So, what will happen is it will go to tau a, unless tau a is equal to b, okay, that will not have that part of it actually. So, what I essentially mean is this part will go to 0, okay, as t goes to infinity. So, we will be left with this tau a part of it, and that is what we see that steady state value is essentially tau a. So, if this is a, this will go to some other value, this is a, this is tau times a, okay, depending on what value you have, okay, that way. Okay. So, this is what is written here. I mean unity step response and all that if you talk about, that is a very standard analysis now. So, what happens if I put a equal to really 1 here, okay. Then we discuss about like a very standard form of solution, it will go towards that anyway. So, it is look the response plot will be something like this, and this is remember this capital T is tau here in this plot. So, we first tau will have 63.2% there, and then 2 tau will approach something like 86.5%, 3 tau 95%, 4 tau 98.2%, things like that. So, if you it will never be exactly equal to that anyway. Okay. So, what the idea here is, let us talk about 4 tau being very close to the value that we really want, 98.2% already. So, that is the type of definition that we bring in, that we tell it, okay, this is the settling time actually, because once it goes there it cannot come out anyway, that is the nature of the thing, it will just remain within that bound actually. So, we will take 98.2%, the very standard definition sort of thing. So, then we will tell, okay, that is the time what is by which the solution really settles. So, that means it is actually settling time actually. Okay. Sometimes people use 3 t or 3 tau as settling time also, assuming that 95% is good enough actually. But by default, if nothing is told to us, then we will take 98.2 as our standard definition actually. So, settling time is 4 tau roughly. So, this is all about first order systems. If you have different type of inputs like sinusoidal and all, you can still talk about different solutions and all, that is not very difficult to derive. So, once you know the particular solution, there are forms available, you substitute it back and derive it actually. So, let us move on to the second order thing, because remember this is also a kind of a review class. So, I will not talk too much detail about all that actually. Homogeneous systems, first we will start in second order system as well, and remember this in a standard form, this A what you see here is taken as 2 zeta times omega n, and B is equal to omega n square. Okay. So, we now what is the approach? I mean we cannot really directly go and solve it. So, what we do is there is a kind of some sort of a theorem available to us for linear system, especially for linear system that is valid in general, which talks about uniqueness. That means if you get one solution, that is the solution, that means there cannot be any other different solutions anyway. So, let us start with a guess solution and see whether that becomes a solution, and if it really becomes a solution, then we are done, because that is the only solution that we can have actually. Okay. So, we essentially get inspired by the solution form what we really had before, that okay, this is the form actually, right. I mean, x of t is e to the power something times t into x 0. So, whether that kind of solution really satisfies the second order form or not, let us start guessing that way. That is the motivation, that is the inspiration for guessing that solution also. So, lambda is arbitrary constant at this point of time, and we are simply guessing that okay, that can be a solution perhaps actually. So, let me explore that. So, now next step is just to substitute it back in there, because the form is already known to us. So, once we substitute it back, we will get this kind of a equation, and since we know that e to the power lambda t is never equal to 0, there will be always some sort of inequality sort of thing, it is never equal to 0, but we still want this equation to be equal to 0. So, the only way that can happen is the coefficient going to 0, and then the coefficient going to 0 is something called characteristic equation. Okay. So, if I am able to find a solution satisfying this equation, this quadratic equation, then I am essentially satisfying this equation, and hence I am satisfying that equation anyway. Okay. So, let us find out what values of lambdas are satisfying this particular characteristic equation, and obviously this is a quadratic equation. So, I will get a solution in this form. Okay. And hence this gives me some sort of a dilemma here, that whether these roots what I are getting are they repeated, or are they real, or are they complex conjugate. Remember, if it is a polynomial with real coefficients, then the solutions from in this form should have complex conjugate pair, if at all they are complex. If they are not complex, that is fine, but if they are complex, they must be conjugate pairs actually, provided this polynomial has real coefficient. That is the thing actually. Okay. So, assuming a and b are real numbers, that has to that is where we will lead to actually. So, let us analyze the case by case. That means, if a and b are real, then there are just kind of 3 cases, and the first is the real and distinct and real roots. Okay, that will happen when this fellow is actually positive. So, the square root of that is also some sort of a positive number actually. Okay. And then there will be complex conjugate, that means inside the square root we have a negative quantity. So, then it will arise to some sort of a complex conjugate pair. And then if it is there can be a third case where it is real, but double roots. That means, if this is a square is equal to 4b, then this part is not there. So, you have a solution which is actually double roots actually. Alright, so let us talk about case by case here. So, we have a distinct and real case first. So, we have x1 taken as lambda 1 t and x2 is taken as lambda 2 t, because these are distinct and real anyway. So, these are something like baseline solutions or the basis solution sort of thing. So, in general we will have C1 times x1 t plus C2 times x2 t. Okay, when this is actually a kind of principle of superposition, we are taking advantage in an indirect way. So, we have 2 basic solutions. So, we want to compose some sort of a function which is C1 x1 plus C2 x2 sort of thing, where C1 C2 are constants. So, that is the general form of solution for the homogeneous part of it anyway. So, we have a solution which is C1 times e to the power lambda 1 t plus e to the C2 times e to the power lambda 2 t. Okay. So, that is our solution in general. Now, remember this is a special case where we discuss about distinct and real roots, and if you have initial conditions known to you properly, then you will substitute it back. Remember, this is a second order differential equation, that means you need 2 initial conditions, both x and x dot probably. So, we substitute it back and then find out C1 C2, that is the standard way. And then we have the second case where it is complex conjugate pairs, then what do you do? Okay. So, if it is complex conjugate, I will be able to express lambda 1 as sigma plus j omega and lambda 2 as sigma minus j omega, that is the complex conjugate pair. So, I go back to my solution, basic solution sort of thing. So, x1 is this part of it. So, I will be able to decompose this, telling that okay, it is e to the power sigma t plus this de Moivre's theorem is there in complex analysis. So, e to the power j omega t is cos omega t plus j sin omega t, I will be able to write that actually. Okay. And similarly, x2 is e to the power sigma minus j omega t. So, that I will be also able to write it in that form. So, essentially I am getting a solution of that form which is very similar to the form that we already have here for the distinct and real. However, the basic solutions are kind of containing these exponential terms which has these complex numbers in there. That means, in this form the solution looks as though it is a complex solution really, and typically I will not be very comfortable to deal with that. So, here we will do little more algebra, telling that okay, if this is in general form, okay, if x1 and x2 are actually some basic solutions, then any linearly independent sort of combination, okay, that will also become a basic solution. So, I am forming something like linearly independent terms where x1 plus x2 by 2 and x1 minus x2 by 2j. If I do that, these two are actually linearly independent terms anyway. So, that will essentially lead to that if you do this algebra, x1 plus x2 means this term will go, and x1 I mean minus x2 by 2j means j part will also go there. Okay. So, you can do this simplification of the algebra yourself, and then tell okay, this is e to the power sigma t cos omega t, and this will e to the power sigma t sin omega t. So, instead of taking this complex solutions as it is, I am just forming some sort of a linear combination, but there are linearly independent terms, and then taking those terms as kind of my basic solutions, around which I will form my general solution. Okay. So, then I am ready with that. So, what I am telling now, my general solution is A times this basic solution plus B times this basic solution basically. So, and essentially what I am telling is okay, this is my general solution, x of t is e to the power sigma 2 sigma t whole into a cos omega t plus b sin omega t. I mean that is what I am interpreting actually. Okay. So, that is how, but this is actually a very real solution, there is no complex term out here actually. The solution that we really get are actually real solutions, even though we have some complex numbers in this form of the solution. So, that is the motivation of getting out of that actually. Now, some sort of analysis of this response, if you really have this kind of a solution there, then it has an exponential term and there is a sinusoidal term. Okay. And we all know that if there is no for a moment, if you consider this sigma as 0, then it is essentially a cos omega t plus b sin omega t. So, that is actually undamped solution which will keep on oscillating like a sinusoidal wave actually. Okay. And then this e to the power sigma t will serve some sort of a envelope for that. Okay. That means, this sinusoidal component will lead to this oscillatory component, but this oscillatory component is supposed to decay, and that decay is given by e to the power sigma t. Okay. Suppose sigma is negative, then this entire solution will eventually go to 0, no matter what kind of oscillations you have actually. Okay. So, these are analysis of the solution that we already have. Okay. So, this part is like sinusoidal oscillation generated by imaginary part of the complex pole pair, and this is the exponential decay what is dictating that the decay of the peak value actually. If you just join the peak values, then it will turn out to be nice decay function actually. Now, we will move on to case 3, where we really have a double root, then what you do? That is the last one that is left out probably. So, in this case we have a lambda 1 equal to lambda 2 equal to lambda, that means we have only one solution. So, obviously we have one basic solution, but this remember this is a second order differential equation. So, essentially we need two basic solutions actually. So, how do you find out that this is this x2 of t basically? Okay. Then one method is the method of variation of parameters, that means we essentially take help of the x1 to find x2, I mean that is the whole idea basically. So, we have x1 available to us already, and let us assume x2 as some parameter u of t. Remember, this is not really a constant quantity, this is also a function of time, some u of t into x1 of t, and again this is our guess at this point of time. Okay. We are just assuming that whether we can really find a solution like that actually. So, now we can substitute x2 dot, we can carry out the algebra u times x1 dot plus u dot times x1, that is what we have here. Then x2 double dot, from taking the help of this one, we will have u times x1 double dot plus u dot times x1 dot, and from this one it is u dot times x1 dot and u double dot times x1. So, this is simple algebra at this point of time, assuming that. Now, we have the term, we have x2 double dot expression, we have x2 dot expression, we have x2 expression as well. So, assuming x2 as a solution, we should be able to go back to the differential equation and try to substitute it back in there. Okay. So, we will do that and then carry out the algebra, and then it turns out that okay, we will be able to write it in this form. There is u multiplied by certain quantities taken together, then u dot I am taking common. So, it will turn out to be like that plus u double dot times x1 equal to 0. Then the beauty part of it is, remember, there are all x1 components actually within the bracket. Okay. and x1 is already a solution, right. So, if x1 is already a solution, okay, then obviously this part is essentially 0, because that's the solution already. So, that's what we have written here actually, okay. That's what is the solution here. So, this entire term is as if it is not there, it is not playing any role here, okay. So, you are left out with only these terms actually, okay. And let us see further some analysis sort of thing. You have x1 dot is okay, you have x1 as e to the power lambda t, right. That is what x1 is a solution, but okay, just a second, okay. But x1 we have already known that okay, x1 is e to the power lambda t. Remember lambda 1 t, but lambda 1 is lambda here. So, if you have x1 as lambda t, okay, if x1 is lambda t, okay, then we have this x1 dot as lambda times e to the power lambda t. I mean, this is the simple algebra actually, okay. Then okay, then what is happening if I multiply both sides by kind of lambda times x1 dot is actually lambda square times e to the power lambda t, and it will again turn out that it is nothing but minus a by 2 times x1 actually, okay. You can I mean you can substitute it back x1 dot I mean that equation and all that, and then you can get it this expression right here actually. So, what you are telling x1 dot is actually essentially minus a by 2 times x1 basically, because that algebra tells us right here x1 dot is lambda times e to the power lambda t, and e to the power lambda t I am kind of substituting it back, getting into that form sort of thing. Then what I am having here is 2 times suppose I just consider the first one and the last one. So, what I am having here is 2 times x1 dot plus ax1 is equal to 0, okay. That is what I am getting here. That means, this term is also 0 basically here, okay, sorry. Okay. So, that means, what I am getting here is this term is also 0. So, what I am left out is simply that last term, and that last term is essentially what I will carry on further actually, okay. So, that last term is u double dot plus x1 is equal to 0, that is the solution that I am getting, that is the equation that I am getting from here. And then we all know that x1 e to the power lambda t which is not equal to 0, right, x1 is really not a trivial solution. Then we are left out with u double dot is 0, okay. So, if u double dot is 0, obviously u dot is a constant quantity, I mean u and then u of okay, if u double dot is 0, then I can really get some solution something like that, u is equal to some constant quantity sorry u dot, okay, and u is equal to some constant quantity, let us say c times d, something like that will happen, okay. Then that is the general form. However, I am interested in this exercise about a particular solution, in other words about a kind of a baseline solution about which I will form linear combination actually, okay. So, this point of time I am just interested in one particular solution which will give me some x2 which is independent of x1, that is all of my motivation here in this exercise basically, okay. So, I will assume d equal to 0, okay, and c equal to 1, that is my choice actually for my simplicity. So, I am essentially left out with ut as nothing but t basically, okay. So, what I am getting here x2 is t times x1, that is how I started with. So, I am getting x2 is t times e to the power lambda t. So, I have got x1 and x2 are kind of linearly independent now, and x2 this particular x2 will satisfy the differential equation also. So, I really have two independent solutions to begin with, and hence my solution is a combination of those two solutions. So, c1 times x1 plus c2 times x2. So, essentially if I put it back there, then it becomes x1 x of t is equal to c1 plus c2 times t into the e to the power lambda t. So, what it essentially means, suppose lambda is 0, that means I have actually kind of a I mean that pole 0 we will see later, but suppose the solution part of it lambda is equal to really 0, that part of it, then this is essentially I mean 1, okay. So, I am left out with c1 plus I mean c1 plus c2 t, and then that one will so essentially what it means is as t goes to infinity, the solution will also go to infinity, not necessarily in an exponential way, but at least in a polynomial way, but still it is going to infinity anyway, okay. That means this particular solution is also destabilizing. So, if you have double poles in the origin, we will see what is poles and zeros later probably next class. So, if you really have double poles in origin, then it will have kind of unstable property basically, the solution is unstable. And in general, if you really want to generalize, that means third order equation, fourth order equation, things like that, and lambda is still 0. So, you will essentially you will add one more term. So, C1 plus C2 t plus C3 t square by 2, something like that will happen in a series way, and then it will actually go to infinity in a polynomial manner. That means, in general, if you have multiple poles at the origin, then the solution is certainly destabilizing. Okay. So, that will see, I mean, that is a kind of a consequence of this analysis essentially. So, in summary, there are two cases, we have distinct and real case, we have complex conjugate, we have real double roots. So, the basic solutions are something like this, okay, if you e to the power lambda 1 t, e to the power lambda 2 t, or these two or that two, and then the general solution turns out to be in this form. That is the summary part of it as far as homogeneous equation is concerned. Now, going to the example sort of thing, this actually homogeneous system anyway. So, we start with this equation. So, we substitute it back, the characteristic equation turns out to be like that, and this is like lambda minus 2 whole square equal to 0. So, that means lambda is equal to 2 2, that means it is real and repeated also, and these are the initial conditions that we are dealing with. So, this is the general equation, general form of the solution that we know. Okay. Then we x dot we can carry out, and then we will substitute these initial conditions what we know, and then solve for this C1 and C2. So, C1 turns out to be 3 and C2 turns out to be minus 5. We can very easily do that in pen and paper, yourself you can do that probably. Then the entire solution turns out to be 3 minus 5 t into e to the power 2 t, and that is the solution essentially. That is how you get the complete solution in accounting for this initial condition as well. That is about it. Then we move on to particular solution. So far we have been talking about second order equations, homogeneous part of it. Now, suppose you have a particular forcing function essentially f of t, and remember this kind of equations are very useful in control theory, because later on we are mainly interested in designing this f of t. That is the control problem essentially. So, given an f of t, we know how to find a solution, but later we will see how to design these forcing functions, so that this differential equation behaves in a way that you really want it to behave. Okay. So, that is I mean that is kind of an inverse problem, but all control problems are typically inverse problem actually. Okay. But we will not worry about that part of it right now. We will discuss, okay, suppose given a function f of t in specific forms, then what is the solution? And essentially this again there is a method of undetermined coefficient, okay, that there are various methods available for standard functions actually. So, we will just talk about undetermined coefficients. So, this particular, suppose you have a term f of t like this exponential term, then you also select an exponential term that way. Remember, e to the power p t also result in e to the power p t, it does not, the exponential part remains same. Okay. Now, if you have a polynomial thing, okay, k to the power k t to the power n, then you account for the polynomial starting from t to the power n, okay, then t to the power n minus 1, n minus 2 all the way up to t to the power 0. So, if you have just one term here, it will lead to entire term there, okay. That is the idea there. Then if you have either cos or sin or any combination of that, then it will essentially you have to account for both sin and cos together. If it is cos, you cannot talk only cos here, it has to be cos and sin. If it is sin also, it has to be cos and sin together basically. So, all these coefficients that are popping up here, okay. For example, this a and b here, and then k n minus 1 all sort of things there, all those things becomes undetermined at this point of time. So, we have to substitute these solutions back into the differential equation, that will result in some sort of a, I mean the coefficient it being equal to, you have to make it equal to 0 sort of thing. So, you have to get some number of equations will pop up as number of unknowns actually. So, then we will be able to solve it from there. So, we will quickly go through a small equation, I mean small example here, and that example is something like this. See this x double dot minus 3x dot plus 2x equal to something like that. So, homogeneous part we will assume that we know already. Okay. Then the particular part is there is a polynomial term, okay, that for that I am assuming some sort of a polynomial starting from t, k1 t plus k0, and there is exponential term. So, there is c times e to the power 3t. So, 3 remains 3 here. So, what are unknowns here? K1, K0 and C really. Okay. So, I will substitute this solution back into the differential equation and then equate the coefficients actually. whatever coefficients will pop up, I will equate the coefficients on both sides and then try to solve it. So, I will solve the solution turns out to be k12, k03 and c equal to half sort of thing. So, the entire solution x p of t is this part of it 2t plus 3 plus half of e to the power 3t. Okay. Remember, the solution, the complete solution is not yet done. That means, you are only getting the particular solution. So, you have the homogeneous solution also there, then put them together x homogeneous plus x particular, then that will have another two constants, that is that C1 C2 sort of thing or A B whatever it is, and then you use the initial conditions that is given to you for the complete solution and then solve for those coefficients actually. Then only you will have a complete solution accounting for initial conditions as well actually. So, that is the procedure actually. Okay. So, that is all about kind of how do you go ahead and get your solutions and all that for linear differential equations both in first order and second order. And before closing this lecture, I thought we will just revisit this second order differential equation from a different perspective very quickly. We will probably do little more in the next class as well. So, if you see classical control books for example, they will typically start with this kind of a differential equation directly. They will not, and this c being the output actually and u being the input part of it. Okay. So, you have c double dot plus 2 zeta omega n c dot plus omega n square c is equal to omega n square times u, that is the standard form. So, if you really talk about this particular standard form where omega n is the natural frequency and zeta is the damping ratio, then we have not discussed the transfer function yet, we will just study about that probably next class. But assume that we can apply Laplace transform here, that I mean most of us know that anyway, then essentially it leads to some sort of a transfer function Cs by Us is in this form, where if I equate this denominator to 0, that is that the solutions of that are essentially the roots. I mean the roots of that equation are essentially the poles of the system essentially. So, a very great amount of study will be done with respect to those poles of the system, because that is essentially which will govern the system stability properties and things like that actually. Alright. So, now let us view that very quickly, we will study in detail probably little more detail next class. So, what will happen in the response nature, if I really start with this particular differential equation, okay, then what is my solution? Solution closed form formulas will be available, I mean these are standard textbook material anyway. But very quickly what will happen is C of t, okay, if I really want to plot it across time, then this is some sort of a graphical idea that that pops up actually. So, what is happening here? There is a very clear cut distinction between what happens for zeta is equal to 0 and zeta is greater than 1 and zeta is equal to 1 and in between basically. Okay. So, if it is zeta is equal to 1, okay, then what happens, it is something called critically damped, okay, that is in between over damped and under damped sort of thing. Okay. But if zeta is equal to 0, that is there is no damping actually. So, essentially this zeta plays a heavy role in damping out the solution, decaying the solutions to 0, because the solution will contain e to the power minus zeta omega n t and things like that, I mean there in the solution part of it if you see that. So, that clearly pops up here okay. So, if zeta is 0, that is really undamped. So, that means the solution will never decay, it will keep on oscillating that way. Okay. And however, if that is anything other than 0, that means let us say it is a number, but it is somewhere in between 0 and 1, okay, then it will have some oscillation in the beginning, but it will essentially decay out later into stabilize somewhere. And if his zeta is greater than 1, there will not be any oscillation, it will almost feel like as though you are operating some sort of a first order system, there is absolutely no oscillation. And zeta equal to 1, that is a very, I mean that is just at the boundary. So, it is neither under damped nor over damped sort of thing. So, but this is a kind of a theoretical thing, I mean in practice zeta exactly equal to 1, it may not happen actually. Okay. So, we will be either in the this side or that side of the story. Okay. So, that is what happens actually. Now, if you really want to analyze the solution little more, then if I really go for this study, I mean the solution response for a step input sort of thing, then the solution turns out to be something like this. Okay. So, if I have time behavior and things like that, typically for under damped system, remember that, because most of the systems are typically under damped, and even though we want to design a control system, we want it to behave like under damped system also, there are variety of reasons for that. Okay. If you really want to make it behave like an overdamped system, the response becomes very sluggish. So, you really do not want to take that much of time to for the system to stabilize and things like that actually. So, typically if underdamped systems are of our interest. So, let us see that a little more closely actually. So, the solution turns out to be something very similar to this. Then okay, there are various concepts. First of all, there is a rise time. Rise time means we start with 10% of the solution and let it go to the 90% of the solution. Okay. So, that part of the time, whatever time it takes to reach that is essentially rise time. Okay. And the peak time is whenever I see the first peak, because the subsequent peaks will be lesser and all that. Whenever I see the first peak, starting from 0, whatever time is gone there, that is kind of a peak time. Okay. And settling time is something very close to the first order system. We essentially monitor the solution and tell, okay, the solution is within let us say 98% of the final solution. However, once it enters, once it is 98%, the subsequent values are within 98% only. I mean, it cannot go beyond that. So, even though the solution enters to this domain here for the first time, I am not accounting for that time actually. I am accounting for that time because subsequently the solution will not come out of this bound. That is the whole idea there. So, that is essentially the settling time here. Okay. And formulas are available in fact. If you know really this zeta and omega n, you essentially know this system kind of you can write this rise time, peak time, settling time from the solution. The solution closed form formula and all that available. We will discuss that probably next class. But from the solution, you can essentially find closed form formulas for these times. So, rise time turns out to be something like this, where beta is an expression. I mean that expression is available to us. Peak time is like pi by omega t, where omega t is damped natural frequency and given by that form. Percentage overshoot is like that, and settling time typically turns out to be like that. Either 2% criterion, that means 98% criterion sort of thing, or 5% criterion means 95% of the final solution. I mean, if I go back to that picture, instead of 98%, I will talk about 95%. So, the settling time will be slightly lesser in that sense. But the default value is probably 2% criterion. So, 4 by zeta omega n. This is not very difficult to remember some of these formulas either. So, settling time is 4 by zeta omega n and peak time is pi by zeta omega t. It's kind of easy to remember actually. Okay. And some of these expressions are actually useful while we design both linear control system as well as nonlinear control system. When you go towards the end of this course, we will see that these expressions are really handy when you attempt to design some control systems actually, because that is the time domain specifications that we will start with. The control design approach will demand that we assure some sort of a settling time and we assure some sort of a peak time, we assure some sort of a percentage overshoot like that actually. So, these little formulas that we are studying right now is not really textbook material in that sense. It is actually used heavily in practice both in linear design as well as non-linear design. So, let us just pay a little more attention at this point of time how these things are so powerful actually. Okay. Now, one more comment that comes in the picture. Let us say I will just plot this percentage overshoot. I have a formula now. Okay, this what is that? Okay, there is a percentage overshoot sort of formula available to me. So, I will take this help of this formula and plot it against damping ratio. Okay, then it turns out that it decays like this. So, that means what it tells me, the moment I increase damping ratio, the percentage overshoot is reducing. So, that means it is good to increase damping ratio. That this plot tells me like that. So, when I design some control system, do I pick up some sort of a high damping ratio? If I really pick high damping ratio, then the percentage overshoot is minimum. But engineering is all about compromise. So, see the next plot, and next plot it turns about, okay, how about plotting some sort of a rise time? I mean, it is kind of a scaled rise time, because rise time into natural frequency sort of thing. This is a constant number anyway. So, rise time will turn to increase actually. Okay. That means, the moment you increase damping ratio, the rise time becomes more and more. That means, the response becomes very sluggish actually. So, on the one hand, you want to have some sort of a less percentage overshoot, but then you have to live with the fact that it takes enormous amount of time to reach there actually. So, you do not want that either. So, you have to select some number which is kind of a good combination of a good compromise between the two, and typical choice turns out to be around 0.7 actually. So, that's kind of okay. Now, just kind of a summary part of it, if you see this pole locations and things like that, Either there can be on imaginary axis, then the solution turns out to be like that, that is underdamped, undamped. And if it is like clearly in the left half side, it is clearly stabilizing. So, it will have a underdamped behavior, okay. It will just oscillate for a little time and then stabilize. If it is a double pole, okay, then there is no oscillation, it will be some sort of a, if zeta equal to 1, that means it is critically damped sort of thing. So, the solution will turn out to be double pole basically. So, anything away from the real line has some damping effect actually, okay. That is the message there. Otherwise, the poles are exactly on the real line, then there is no oscillation, okay. So, the is like critically damped actually, okay. Then if zeta is really greater than 1, then the poles will be distinct on the real line, okay. So, that is when we will have this over damped sort of ideas there. So, the response when you see something like this, you can also guess where these pole locations are roughly, and that is the message here. So, with this summary, probably I will stop here in this part of the lecture. We will carry further this kind of ideas in a transfer function approach in the next class. That we will start with some sort of a review of Laplace transform, and then apply for some differential equation to arrive at a transfer function, and then using this pole 0 ideas we will introduce, and then study the same solution response again, the nature of the solution response and all that in little more detail about what are the variations that you can introduce and what are the implications that you can have as poles move away in particular directions and things like that. We will also introduce zeros of the system later, then tell okay, if there is no zero, that is the response, then if there are zeros, then what happens. Now, we have discussed about first and second order systems here, but systems are not really first and second order, right. We know that they are higher order systems. So, there is the idea of suppose you do classical control design, then considering higher order systems are also we are not capable of handling that in a very good way. So, one approach is dominant poles, that means whether there are like two poles that are very close to the imaginary axis, so that I can really neglect some of these poles that are far away from them. So, those are the concepts that are available. So, we will discuss that in little more detail in the next class.